Hi everyone, I'm glad to present our work optimizing fiducial marker placement for improved visual localization. This is a joint work with Joseph DeGol, Victor Fragoso, Sudipta Sinha, and John Leonard. Visual localization is a foundational capability for many devices, such as AR/VR glasses. However, the accuracy of localization depends on not only software and hardware, but also environments. For robust localization in challenging environments, a common recommendation for users is to use QR code or fiducial markers. Traditionally, these marker positions are selected by humans who are familiar with visual localization techniques. This work explores the problem of automatic marker placement within a scene. Therefore, selecting marker positions requires no human intervention and becomes much more scalable. Visual localization refers to a process that uses a 3D map and a model to localize a query image within the scene. There are mainly two challenges in visual localization. The first one is a similar appearance. For example, the first two images look similar, but they belong to different rooms. The second challenge is textureless areas. Given these challenging situations, a common strategy is to place fiducial markers in the scene. This leads to our problem statement. What are the optimal marker positions for improved visual localization accuracy? In the paper, we reviewed related work for mapping and localization using fiducial markers or other artificial landmarks. A novelty in our work is that we consider both natural theme features and fiducial markers when optimizing marker positions for improved visual localization. Here is a teaser video demonstrating our approach. The algorithm requires a 3D model as the input and then returns marker positions. Here I'm showing you results for two environments, the apartment and the mocap room. The figure in the middle shows that our algorithm updates camera localizability scores over the entire environment. The animation demonstrates that we run multiple loops to optimize marker positions. In each loop, we identify the best marker position that maximizes the localizability score. There are three key elements in our algorithm. The first one is occupancy grid mapping that converts a 3D model to a floor plan of feasible camera poses and marker positions. And then we evaluate camera localizability scores over feasible camera poses. Finally, we use a greedy algorithm to select best markers one by one in a sequence that maximizes the localizability score. A technical contribution in this work is to define the camera localizability score. Specifically, at any camera pose C within the 3D model, we render an image and synthesize measurements Z to simulate a visual localization problem. And then we estimate the probability distribution of the pose given the synthetic measurements. The factor graph here is a graphical model of the distribution. Finally, the entropy of the distribution defines the localizability score. Adding a fiducial marker to the scene introduces new measurements, leading to a new factor graph, a new camera pose distribution, a new entropy, and a new localizability score. The difference between the new and old scores is the information gain that quantifies the impact of the marker placement. In our experiments, we evaluate visual localization accuracy led by different marker placements. On the left-hand side, I'm showing the original floor plan and the new floor plan with markers. As shown in the middle, the test images on the different marker placements share the same set of camera poses. And then we use the same localization system to estimate camera poses of these test images. Here is the recall of test images that are localized within 5 cm and 5-degree errors from the ground truth. We are comparing against the no marker placement, random placement, and the uniform placement along the walls. Adding more markers increases the recall for all placement approaches, but our approach outperforms all the others. You can find the results for more scenes in our paper. We concluded that our algorithm can improve the localization rate by up to 20%. The camera localizability score we proposed manages to identify challenge areas in a scene for visual localization. The work can be extended by exploring new methods for computing the localizability scores and more efficient optimization methods beyond the greedy algorithm. This work was started at Microsoft and extended at MIT. Qiangqiang and John acknowledge the support of these funding resources. Thank you.